Hello everyone, and welcome to me, Learning Rust. Today we'll go over the 7th chapter of the book about managing and growing projects with packages, crates, and modules. Okay. As you write large programs, organizing your code will be more increasingly important. By grouping related functionality and separating code with distinct features, you'll clarify where to find code that implements a particular feature and where to go to change how a feature works. The programs we've written so far have been in one module in one file. As a project grows, you should organize code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates and optionally one library crate. As a package grows, you can extract parts into separate crates that become external dependencies. This chapter covers all the techniques. For very large projects comprising a set of interrelated packages that evolve together, Cargo provides workspaces, which we'll cover in the Cargo workspaces section in chapter 14. Okay, so it's not the entire thing. Okay, we'll also discuss encapsulating implementation details, which lets you reuse code at a higher level. Once you've implemented an operation, other code can call your code via its public interface without having to know how the implementation works. The way you write code defines which parts are public for other code to use and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep in your head. A related concept is scope. The nested context in which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whatever a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item that and what that item means. You can create scopes and change which names are in or out of scope. You can have two items with the same name in the same scope. Tools are available to resolve name conflicts. Okay, so understood. We're going to talk about packages, about managing packages, about multi-files, about managing namespaces. Probably I think the scopes is the namespace we know from C++, C#. Rust has a number of features that allow you to manage your code's organization, including which details are exposed, which details are private, and what names are in each scope of your program. These features, sometimes collectively referred to as module system, include packages, a cargo feature that lets you build, test, and share crates, a tree of modules that produces a library or an executable. Modules and use let you control the organization scope and privacy of paths. Paths, a way of naming an item such as a struct, function, or module. In this chapter, we'll cover all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have solid understanding of the module system and be able to work with scopes like a pro. Okay, let's dive in. Packages and crates. I feel it's going to be a read-heavy episode. The first parts of the module system we'll cover are packages and crates. A crate is the smallest amount of code that the Rust compiler considers at a time. Even if you run Rust C rather than Cargo and pass a single source code file, as we did all the way back in chapter 1. Okay. The compiler considers that file to be a crate. Crates can contain modules, and the modules may be defined in other files that get compiled with the crate, as we see in the coming section. A crate can come in one or two forms: a binary crate or a library crate. So there are source code, open source and closed source crates. Okay, binary crates are programs you can compile to an executable that you can run, such as a command line program or a server. Each must have a function called main that defines what happens when the executable runs. All the crates have created so far have been binary crates. Okay, so binary crates are not closed source. These are crates that are runnable. Okay, library crates don't have a main function and they don't compile to an executable. Instead, they define functionality intended to be shared with multiple projects. For example, the rand crate we used in chapter 2 provides a functionality that generates random numbers. Most of the time when rustaceans say crate, they mean library crate. and they use crate interchangeably with the general programming concept of a library. The crate root is a source file that the Rust compiler starts from and makes up the root module of your crate. We'll explain modules in depth in the defining modules to control scope and privacy section of this chapter, I hope. Packages is a bundle of one or more crates that provide a set of functionality. A package contains a cargo toml file that describes how to build those crates. Cargo is usually a package that contains the binary crate for the command line tool you've been using to build your code. The cargo package also contains a library crate that the binary crate depend on. Other projects can depend on the cargo library crate to use the same logic the cargo command line tool uses. I guess we'll learn about this. A package can contain as many binary crates as you like, but at most only one library crate. A package must contain at least one crate, whether that's a library or a binary crate. Let's walk through what happens when we create a package. First, we enter a command cargo new. Okay, let's create cargo new and my project. Okay, let's go along with it. Cargo new my project. Okay, I just code it. I'll just code into it, and that's it. Okay, and we can see the files, cargo and src, and also have the git ignore, which is not presented in the ls because it's a hidden file. Okay, and then in the source we have this. Okay, after run cargo new, we use an ls to see what cargo creates. In this project directory, there is a cargo toml file giving us a package. There is also an src directory that contains main.rs. Open cargo toml in your text editor and note that there is no mention of main.rs. Yep, no mention. Main.rs. There is no cargo follows a convention that src main.rs is the crate root of a binary crate with the same name as package. Likewise, cargo knows that if the package directory contains src lib.rs, the package contains a library crate with the same name as the package, and src lib.rs is that crate root. Cargo passes the crate root files to Rust C to build the library or binary. Here we have a package that only contains source main.rs, meaning it only contains a binary crate named my project. If a package contains src main.rs and src lib.rs, it has two crates, a binary and a library, both with the same name as the package. A package can have multiple binary crates by placing files in src bin directory. Each file, do we have an src bin directory? No. And multiple. Each file will have a separate binary crate. Okay, I still don't get it fully what they mean, but let's read on and look at some examples. In this section, we'll talk about modules and other parts of the module system, namely paths that allow you to name items, the use keyword that brings a path into scope, and the pub keyword to make items public. We'll also discuss the as keyword, external packages, and the glob operator. First, we're going to start with a list of rules for easy reference when you're organizing your code in the future. Then we'll explain each of the rules in detail. Here we provide a quick reference on how modules paths, the use keyword, and the pub keyword work in the compiler, and how most developers organize their code. We'll be going through examples of each of the rules throughout this chapter, but this is a great place to refer to as a reminder of how modules work. Okay. Start from the crate root. When compiling a crate, the compiler first looks in the crate root file, usually src lib.rs for a library crate or src main.rs for a binary crate for code compile. Declaring modules. In the crate root file, you can declare new modules. Say you declare a garden module with mod garden. The compiler will look for the module's code in these places. Inline with curly brackets that replace the semicolon following mod garden, So I guess I can do, let's just, I can declare a module like this, like mod garden, and just go and declare this module inline in a src garden rs or in garden folder with mod rs. Okay. We'll learn about modules in the future, I think. Okay. Declaring submodules. In any file other than the crate root, you can declare submodules. For example, you might declare mod vegetables in the src garden rs. The compiler will look for the submodules code within the directory named for the parent module in these places. Okay, let's see. We can do it inline as before, and we can do garden vegetables and garden vegetables mod. Okay, so submodules are like subdirectories inside the source tree. Okay, path to code in modules. Once a module is a part of your crate, you can refer to code in that module from anywhere else in that same crate, as long as the privacy rules allow. Using the path to code, for example, an asparagus type in the garden vegetables module will be found at crate garden vegetables asparagus. Private versus public. So I guess modules is like namespaces. Maybe. Private versus public. Code within a module is private from its parent modules by default. By its parent modules by default. To make a module public, declare it with a pub mod instead of mod to make item within a specific module public as well. Use pub before their declarations. Okay, so if I use this, then I can use it only here and maybe submodules. And if I do this, I can also include this, well, if it was a librs, and use it outside. Okay. So by default, it's private. Good to know. The use keyword within a scope. The use keyword creates shortcuts to items to reduce repetition of long paths. In any scope that can refer to create garden vegetables asparagus, you can create a shortcut and use create garden vegetables asparagus. And from then on, you only need to write asparagus to make use of that type of scope. Yeah, makes easier. It's like a use in C++. Okay, here we create a binary crate named backyard that illustrates these rules. The crates directory, also named backyard, contains these files and directories. Okay, should we create this? No, I don't think there's a lot of things here, so let's just read through it. So we have a folder named backyard with a cargo and source with a main rs, garden rs, and garden vegetables rs. So I guess before reading on that we have like a main that uses a module called garden, and there's a submodule called vegetables in the garden. So let's look at the main. Yeah, I have a public module garden, and I use asparagus from the garden vegetables. I can use it. The pubmod garden line tells the compiler to include the code it finds in src garden rs, which is src garden rs. Pubmod vegetables, and here pubmod vegetables means and this is the code. Yeah, let's do something like this. We'll keep the main, but then we'll declare first of all, let's create a new file here and create a garden.rs. We have a garden.rs. We'll add a new folder here that's called garden. And then here we'll create a new file called vegetables.rs. Now, vegetables.rs has a hashtag derive bug. Yeah, and it has a pub struct asparagus. So I'm just defining an empty struct called asparagus. In the garden, I'm just using pub mod vegetables. Will it autocomplete? No. And then in main, I can declare pub mod garden, right? And I can do a use create garden vegetables asparagus, and semicolon. In here in the source code we have let plant equals asparagus. I can use it, and then I can print hello world plant. Okay, let's try to run this. Trying to run this. Cargo run. Okay, hello world asparagus. Great. So from what I've learned, I can, instead of using garden rs, I can use something else. I can use mod rs here. If I create a new file, mod rs here, instead of this garden, I can declare vegetables here and delete this. Right, and it should still work. Let's try this. Yeah, it still works the same. So what I did, instead of having garden rs, inside the garden folder, I had the mod rs, which defines everything related to garden, and then we have the vegetables that declares a submodule for this. Okay, let's continue. We have this, we have this. Now, grouping related code in modules. Modules let us organize code within a crate for readability and easy reuse. Modules also allow us to control the privacy of items. Because code within a module is private, by default, private items are internal implementation details not available for outside use. We can choose to make modules and the items within them public, which exposes them to allow external code to use and depend on them. So basically, if I go to vegetables and I remove this public, this will be, illegal to do. So I need to put the public here. If I remove public from this, then the vegetables will be illegal. Great. And if I remove the public here, nothing should happen. Yeah. Excellent. As an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signatures of functions, but leave their bodies empty to concentrate on the organization of the code rather than the implementation of the restaurant. In the restaurant industry, some parts of restaurants are referred to as front of house and other as back of house. Front of house is where the customers are. This encompasses where the host seats customers, server take orders and payment, and bartenders make drinks. Back of the house is where the chefs and cooks work in the kitchen, dishwashers clean up, and managers do administrative work. To structure our crate in this way, we can organize its functions into nested modules. Create a new library named restaurant by running cargo new restaurant -- lib. Okay, this is a new thing. I think we'll close this and then create a new cargo new restaurant -- lib. Great. I've created this. Let's go to let's open it up. Let's see what's the difference here. Now we have librs with tests and an add function. Okay. Let's continue. Okay. Then enter the code listing in 7.1 into librs. So we delete everything here and then create module front of house I have a module hosting that has a function. That has a function name add to waitlist and a function name seat at table. Okay, and we have second module called serving. Serving that have a function called take order. I have a function named serve order and a function named take payment. Great. Okay. So we have a module and then two submodules. Everything is private still. Let's continue. We define a module with the mod keyword followed by the name of the modules, in this case front of house. The body of the module then goes inside curly brackets. Inside modules we can place other modules, as in this case within the modules hosting and serving. Modules can also hold the definition for other items such as structs, enums, constants, traits, and, as in listing 7.1, functions. By using modules, we can group related definition together and name why they're related. Programmers using this code can navigate the code base on the groups rather than having to read through all the definitions, making it easier to find the definitions relevant to them. Programmers adding new functionality to this code would know where to place the code to keep the program organized. Earlier we mentioned that source main RS and source lib RS are called crate roots. The reason for their name is that the content of either of these two files form a module named crate, and the root of the crate's module structure known as the module tree. Listing 7.2 shows the module tree for the structure in 7.1. So we have a crate, which is the lib RS. We have a module named front of house, and then we have two submodules hosting and serving, which has these 5 functions. Okay, and this tree shows how some of the modules nest inside one another. For example, hosting nests inside the front of house. The tree also shows that some modules are siblings to each other, meaning they're defined in the same module. Hosting and serving are siblings defined within front of house. If module A contained inside module B, we say module A is the child of module B, and that module B is a parent of module A. Notice that the entire module tree is rooted under the implicit module named crate. Yeah, we saw this crate from the use in the previous page. The module tree might remind you of the file system directory tree on your computer. This is a very apt comparison. Just like directories in a file system, you use modules to organize your code, and just like files and directory, we need a way to find our modules. Okay, nothing about them being private yet. Next page. Path for referring to an item in the module tree. Interesting. Yeah, it's also interesting what about the privacy and publicity of sibling modules. Okay, to show Rust where to find an item in a module tree, we use a path in the same way we use a path when navigating a file system. To call a function, we need to know its path. A path can take two forms: an absolute path in the full path starting from the crate root, as we saw in the use in the previous page, in the previous 2 pages. For code from an external crate, the absolute path begins with the crate name, and for code from a current crate, it starts with a literal crate. A relative path starts from the current module and uses self, super, or an identifier in the current module. Okay, both absolute and relative paths are followed by one or more identifiers separated by double colons. Returning to listing 7.1, say we want to call the add to waitlist function. This is the same as asking what's the path of the add to waitlist function. Listing 7.3 contains listing 7.1 with some of the modules and functions removed. We'll show 2 ways to call the add to waitlist function from a new function, eat at restaurant, defined in the crate root. These paths are correct, but there is another problem remaining that will prevent this example from compiling as is. We'll explain why in a bit. The eat at a restaurant function is a part of our library creates public API. Library creates public API. So we mark it with the pub keyword. In the exposing paths with the pub keyword section, we'll go into more details about pub. Okay, so we have this. I'm not going to remove the functions, but I'm going to add the public function eat at restaurant. And then the absolute path is create front of house hosting add to waitlist. And then we can do front of house, which is this function hosting add to waitlist. Let's try it with a super. Let's see if I have a super here. Super, no. Oh, okay. No, nothing. And if I do self, I have self, front of house, hosting, okay. Add to waitlist. I just add the previous one, which is just front of house, hosting, add. Okay, so I have 3 ways of accessing this function now. Okay, and also because this is private, let's just try fixing this. Now this should be public and everything is okay except the warnings. Great. Okay, the first time we call the add to waitlist function in the eat at restaurant, we use an absolute path. The add to waitlist function is defined in the same crate as eat at restaurant, which means we can use the crate keyword to start an absolute path. We then include each of the successive modules until we make our way to add to waitlist. We can imagine a file system with the same structure. We'd specify the path, front of house hosting add to waitlist, to run the add to waitlist program. Using the crate name to start from the crate root is like using / to start from a file system root in your shell. The second time we call add to waitlist in the eat at restaurant, we use a relative path. The path starts with front of house, the name of the module defined in the same level of the module tree at eat at restaurant. Here the file system equivalent will be using the path front of house hosting add to waitlist. Starting with a module name means that the path is relative. Okay, so and we also showed that we can use self. I think self is good when you want to be very implicit about what your path is and not rely on someone not adding something that will conflict with this. Okay, choosing whether you use a relative or absolute path is a decision you'll make based on your project and depends on whether you want you're more likely to move item definition code separately from or together with the code that uses the item. For example, if we move the front of the house module and the eat at restaurant function into a module named customer experience, we'd need to update the absolute path to add to waitlist, but the relative paths would still be valid. However, if we moved eat at restaurant function separately into a module named dining, the absolute path of the add to waitlist call would stay the same, but the relative path would need to be updated. Our preference in general is to specify absolute paths because it's more likely we'd want to move code definitions and item calls independently of each other. I think that the compiler will alert us when we do an error regarding this. Let's try to compile. It won't compile. We'll get errors probably about private. Yeah, so we need to add the public. The error message say that the module hosting is private. In other words, we have the correct paths for the hosting module and the add to waitlist function, but Rust won't let us use them because it doesn't have access to the private sections. In Rust, all items, functions, methods, structs, enums, modules, and constants are private to parent modules by default. If you want to make an item like a function or a struct private, you put it in a module. Items in a parent module can't use the private items inside child modules, but items in child modules can use the items in their ancestor modules. This is because child modules wrap and hide their implementation details, but child modules can see context in which they're defined To continue with our metaphor, think of privacy rules as being like the back office of a restaurant. What goes on in there is private to restaurant customers, but office managers can see and do everything in the restaurant they operate. Rust choose to have the module system function this way so that hiding inner implementation details is the default. That way you know which part of the inner code you can change without breaking outer code. However, Rust does give you the option to expose inner parts of child module's code to outer ancestors module by using the pub keyword to make an item public. Yeah, it's okay. Like it doesn't matter. I personally don't care that way or another about public-private things. I don't care if everything is public, as long as there's a good code structure and good naming conventions. But yeah, it could be helpful for compilation, for error mitigation. Yeah. Exposing paths with the pub keyword. Let's return to the error in listing 7.4 that told us that the hosting model is private. We want the eat@restaurant function in the parent model to have access to the add to waitlist function in the child module. So we mark the hosting module with the pub keyword as shown here. This still will not compile. We need to add this to the function. Probably what happened, adding the pub keyword in front of mod hosting makes the module public. With this change, if we can access front of house, we can access hosting, but the content of hosting is still private. Making the module public doesn't make its content public. The pub keyword on a module only lets code in its ancestor module to refer to it, not access the inner code. Because modules are containers, there are not much we can do by only making the module public. We need to go further and choose to make one or more of the items within a module public as well. Yeah, that's basically what we did. The error in listing 7.6 say that the add to waitlist function is private. The privacy rules apply to structs, enums, yada yada. Let's also make the add to waitlist function public and add the pub keyword. Okay, that's what we did. Okay, now the code will compile. See why adding the pub keyword let us use these paths in add to waitlist with respect to the privacy rules. Let's look at the absolute and relative paths. In the absolute path, we start with crate. The root of our crate model is tree. The front of house model is defined in the crate root, while the front of house isn't public because the eat@restaurant function is defined in the same module as front of house. That is, eat@restaurant and front of house are siblings. We can refer to front of house from eat@restaurant. Next is, okay, so siblings can see each other. Next is the hosting module marked with pub. We can access the parent module of hosting, so we can access hosting. Finally, the add to waitlist function is marked with pub, and we can access its parent model, so function call works. Yeah, it doesn't tell us anything new. Okay, in a relative path, the logic is the same as the absolute path, except for the first step. Rather than starting from the crate root, the path starts from front of house. The front of house module is defined within the same module as eat@restaurant. So the relative path, starting from the module in which eat@restaurant is defined, works. Then, because hosting and add to waitlist are marked with pub, the rest of the path works, and this function called is valid. Sorry for reading this fast, but yeah, it's self-explanatory. I can access siblings. A sibling is visible to me. Siblings' children are private by default, and everything else that is not a parent is also private. Okay, if you plan on sharing your library crate so other projects can use your code, your public API is your contract with users of your crate that determines how they can interact with your code. There are many considerations around managing changes to your public API to make it easier for people to depend on your crate. These considerations are out of the scope of this book. If you're interested in this topic, see Rust API guidelines. Okay. We mentioned the package can contain both source main binary crate root as well as src lib rs library crate root. In both crates, we'll have the package name by default. Typically, packages with this pattern for containing both a library and a binary crate will have just enough code in a binary crate to start an executable that calls code with the library crate. This lets other projects benefit from the most functionality that the package provides because the library crate's code can be shared. The module tree should be defined as in src lib. Then any public items can be used in the binary crate by starting path with the same name of the package. The binary crate becomes a user of the library crate just like a completely external crate would use the library crate. It can only use the public API. This helps you design a good API. Not only are you the author, you're also a client. Yeah, it's a good practice to write your usage code as though you don't know the inner workings. It allows you to make better decisions about the API. Also start with the usage code. Yeah, it helps you see what you need from the API when using the library you're designing. Okay, starting relative paths with super. That's good. We can construct relative paths that being in the parent module rather than the current module or the crate root by using super at the start of the path. This is like starting a file system path with a dot syntax. Using super allows us to reference an item that we know is in the parent module, with which can make rearranging the module tree easier when the module is closely related to the parent, but the parent might be moved elsewhere in the module tree someday. Consider the code listing 7.8 that models the situation in which a chef fixes an incorrect order and personally brings it out to the customer. The function fix incorrect order, defined in the back of house module, calls a function deliver order, defined in a parent module by specifying a path to deliver order starting with super. So we have, let's add another module here, back of house, and we have a function fix incorrect order. Let's add the function first, hook order, right? And then here we can hook order and we have a here deliver order. Okay, we have a function deliver order. Okay, I think it should be in the front of house, but never mind. Cook order and deliver order. Yeah. Okay, let's add this by default, but sorry. Super deliver order. Okay. The fix incorrect order function is in the back of house module, so we can use super to go to the parent module of back of house, which is in this case is crate. The route from there we look for deliver order and find it. Success. We think that back of house module and the deliver order function are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the crates module tree. Therefore, we used super so we'll have fewer places to update code in the future if this code gets moved to a different module. So here, super just goes up one module to the crate module and then uses deliver order. Let's see if I can do crate and then deliver order. This also works. Yep, this also works. Great. Making structs and enums public. Okay, I think it's more of the same, but let's read on. We can also use pub to designate structs and enums as publics, but there are a few details extra to the usage of pub with structs and enums. If we use pub before a struct definition, we make the struct public, but the struct fields will still be private. Well, we can make each field public or not on a case-by-case basis. Listing 7.9 will define a public back of house breakfast struct with a public toast field, but a private seasonal fruit field. This module's the case in a restaurant where the customer can pick the type of bread that comes with a meal, but the chef decides which fruit accompanies the meal based on what's in the season and in the stock. The available fruit changes quickly, so customers can't choose the fruit or even see which fruit they get. So let's go over the code. We have in the back of house, we have the public structure. We have a public structure called breakfast. And then we have a public toast, which is a string, and seasonal fruit, which is also a string. Sorry, comma here. Okay. And then I have the implementation of this, of breakfast. We have a public function, summer, that get a toast, the reference to a slice, the string slice, and returns a breakfast. And I create a breakfast with a toast that equals string from the slice, and seasonal fruit will be peaches. Okay, let's just format this a little bit. And the fruit will be string from peaches. Excellent. Okay, so if I run summer, let's try this. Back of house, breakfast, summer. This should work, and the toast will be, I don't know, grain. This should work. Excellent. And if this is not public, I'll get here an error here, and if this is not public, I'll have error nowhere. I guess. Okay. So we have this function is at restaurant. Now we have, let's actually do their implementation. And we have let mutable meal be back of house breakfast summer rye, and then we have meal toast equal string from wheat, and then we have print line of I'd like toast please, and then meal toast. Okay, so now this works. I don't want to run this because it'll have a lot of warnings. But if I change this, I'll not be able to print it, right? Yeah, I don't be able to assign it and print it because it's private. Okay, let's move on. Because toast field in the back of house is public, in each restaurant we can write and read to the toast field using dot notation. Notice that we can't use the seasonal fruit field in the eat at restaurant. Yeah, if I'm doing something meal seasonal fruit, yeah, it's not even, let's see the error here, is private. Yeah. Okay. Also note that because back of the house breakfast has a private field, the struct needs to provide a public associated function that constructs an instance of breakfast. We've named it summer here. If breakfasts don't have such a function, we couldn't create the instance of breakfast in eat at restaurant. Okay, yeah, so it's like a constructor like a factory sort of thing here. In contrast, if we make an enum public, all of its variants are public. We only need the pub before the enum keyword as shown in listing 7. Okay, so I'm not going to check this. I'll trust the book that if I have a public enum, I don't have to make everything here public. I think if I have some sort of things inside the enums, types that associated, they need to be public or at least accessible in order for this to work. Okay, because we made the appetizer enum public, we can use the soup and salad variants and eat at restaurant. Enums aren't very useful unless their variants are public. It would be annoying to have to annotate all enum variants with pub in every case, so the default form of enum variants is to be public. Structs are often useful without their fields being public, so struct fields follow the general rule of everything being private by default unless annotated with pub. There is one more situation involving pub that we haven't covered, and that's our last module system feature, the use keyword. We'll cover use by itself first, and then we'll show how to combine pub and use. Okay, use. I think I would stop here and then continue. This is the next chapter. I think it's a good place to stop. So see you in the next episode. Goodbye.